Yes.
Welcome again to another episode of Shannon channel. So I'm happy today to have Varun Jog with me, and he's gonna give us a great talk on information-theoretic perspectives on learning algorithms.
Okay, thank you, Salim, for inviting me to give this talk. This is a very novel concept, and I'm very excited to try it out. Okay.
So, yeah, so we can start.
Yes.
Right?
All right. So let me share screen and share.
Oh, the infinite
view full screen. Okay. Is that working?
Yes.
Should he maximize? Or? No, this is good. Yeah, this is good.
All right. Okay. All right. I'll start. I was originally thinking that I'll just take my laptop and go sit next to the lakeside and sit in the sun. It's kind of rare to have such nice weather in Wisconsin. But anyway, I thought that might be a bit difficult to achieve logistically. But yeah, it's an exciting concept. So the fact that I had the choice of just sitting wherever I could and give this talk. So yeah, so I'll start. The title of my talk is Information-theoretic Perspectives on Learning Algorithms. This is joint work with my student Adrian, who is in the math department, Ankit, who is a first-year student in the CS department, and Polling Low, whose affiliation is listed at stats, but she's in ECE, stats, math, and industrial engineering. So she picks whichever one she likes. So these are the collaborators. All right, so what is this talk about? So essentially, I want to start with kind of the simple problem of what do we mean by, say, fitting a curve. Right, so in the image, I have a bunch of points, and our job here is to fit a curve that passes through all these points. And this seems like a fairly standard kind of a learning problem. You just have points, you learn what curve fits it. And this is what I'll call as the forward problem. So by forward, I just mean you're given a data set and you want to get a curve at the end of it. And often in these kinds of problems, we want to try and find what is the right fit. So on the left, you see an image where something like a quadratic has been fit to those points. And on the right, we have this kind of a really wiggly curve that makes a big effort to pass through each and every one of the data points. So intuitively, we know that the thing on the left it seems like a proper fit, but the curve on the right is kind of overfitting. And we know like visually that that's what is happening. And one intuitive explanation is too wiggly. It shouldn't be so wiggly. It has to be something smooth like the one on the left, right? And but of course, too wiggly is not a mathematically accurate term. So if you want to give like an accurate term, the way to describe it is that the function on the right is not stable. By that I mean that if you were to change your x coordinate by a little bit, then the y coordinate may change by quite a bit. In some sense, the derivative is not bounded, and you cannot really easily bound how much y might change if you were to change x by a little bit, which is not a problem for the curve on the left. So the curve on the left is what we say it's a stable kind of a curve, and on the right we say it's not stable. So now I want to kind of describe what is the reverse problem, which is you are given the curve, and now your job is to guess the points from the curve. Right. So here are the same two curves from the previous slide. On the left, we have this nice quadratic. On the right, we have the wiggly curve, and that's what we are trying to solve. Given curve, find the endpoints. Now, clearly, so this is what I call the backward problem, and you can kind of see that if you want to solve this problem, it's much easier to solve that problem for the curve on the right than it is for the curve on the left. And that's because if you look at the curve on the right, you'll see that, well, there's no reason why this curve must have gone here. the only reason it went there was because it was trying to fit a point there. Then it started to go up, and the only reason it went there must have been because it was trying to fit a point there, and so on. So if you see a super wiggly curve, then you can kind of guess where the original points would have been, because it is just trying to fit all the points. But if you look at on the left-hand side, there's no such indication of where the points were. You can guess that they were in some general position along that curve, but you don't exactly know where those points were, right? So the rough, I guess, one-line explanation for why this is happening is somehow the curve on the right just has more information about the data set than the curve on the left, right? So this is something that I want to explore more in this talk, that there is some relation between information and overfitting. So if the curve on the right had clearly exhibited overfitting, and it also happened to have more information about the data point, so there is some connection between information and overfitting. So I want to explore this connection a bit in this talk. Then I will introduce what is called generalization error in machine learning algorithms, and basically show how to analyze this error in some special class of learning algorithms. And thirdly, I'll show how to study this generalization error, not exactly using information theory, but using what is called optimal transport theory. There is some motivation for using optimal transport theory, and that is because sometimes information theory is not the best tool, because the quantities that we end up using in information theory, like KL divergence and entropy and mutual information, they are not always that well behaved, in the sense that they can shoot up to infinity sometimes, and that's why they are not always the best things to use. So that's why I'll try to present something that uses this other optimal transport theory to give different kinds of bounds. And I learned with some speculations and open problems. Right? Cool. So feel free to interrupt me. I don't have visual feedback, but if you just unmute your microphone and talk, I'll be happy to pause and respond.
Sure.
All right. So we want to use information theory for analyzing learning. So information theory deals with channels and communication. So where do we get a channel here? So here's the channel. So one way to think of a learning algorithm is it takes as input a data set. So S is what I call the data set. It's taking as input a data set. And there is some black box magic algorithm. Data sort of gets fed into it, and out comes whatever desired output. So in this case, the output is the curve W. So the input is a bunch of points. Output is this green curve. Right. So the way I'm thinking of the output right now is it's some point in R to the D. So of course, when you think of a curve, you might think, well, a curve can be really arbitrary. It doesn't have to be R to the D. But roughly what you can think is, let's say we are trying to fit polynomials of a certain degree T. So then it's just a finite dimensional. The curve is characterized by a finite number of kind of parameters. So that's the way I'm trying to think of this output W. So we have an input S, and then we have n IID samples. So we assume that the thing that is getting fed to our algorithm is IID samples. Each sample is distributed according to mu. So what's going in is a product distribution. The algorithm looks at these endpoints, does something, and then produces a W. So the channel here is basically the algorithm. The channel is given an S, you're producing a W, and it's doing something to do that. So the channel is just probability of W given S. It's this conditional probability. And it's different from regular communication channels, because in regular channels, the channel is what is given by nature. There is Gaussian noise, or there is a binary symmetric channel. So that is something that you cannot really tinker with. You can only do stuff on the coding side. So you can design clever codes that get rid of the uncertainty because of the channel.
Varun, I have a question. So do you have a probability distribution here because the algorithm is randomized, or?
Yeah. So
the data is randomized. So
right. So that's a great question. So So the way I'm thinking is like, you might have a deterministic algorithm, so something like regression, where you look at the points and out pops out a slope.
Yes.
And that's like a specific formula with no randomization in it. I would still think of it as a channel where you have a delta distribution on the desired output.
Okay.
But of course, in general, if you're using something like a stochastic gradient descent or Langevin dynamic, if you're using some algorithm which does not look at the whole n data set, but maybe looks at random chunks of it to make iterative updates, then you're going to land up at some w, which is going to be a random function of x's. It won't be deterministic. So yeah, that's why it's being modeled right now as a channel from as I guess a random p of w given s instead of just a deterministic w as a function of s. All right. Okay, and all right. So so the goal here is to design the algorithm, which is designing the channel. But for what purpose? Well, the purpose is to minimize some kind of a loss function. So that's what we often do in learning. We design some loss function, then say that we want a bunch of parameters, or we want an algorithm to be such that this loss function is minimized. So what is a loss function? Well, a loss function takes as input w, which is say the curve, and a point x, and then says, well, it's some measure of how far away you are from the curve, say, or it can be any arbitrary loss function. So you have a loss function which is on this cross on the space w cross x and goes into R. And of course, what's the best w that one would like to choose? Well, if you look at this term, the expected value. So the expected value is you are finding out what is the expected loss for a point x that is drawn from the true distribution. So let's say x is the set of images, let's say a set of cat images. So and w is some classifier. So then L of wx is saying, well, if you were to run this classifier on the true distribution from which data is being generated, then what's the loss that you experience? And if that loss is minimized, then of course you should choose that w star, which is the best possible choice for this optimization problem. Unfortunately, this problem is not easy to solve, and that's because we don't really know this distribution mu. So all we know really is that all we have is a bunch of n cat images, and from n cat images we are supposed to do something. But those n images may not give us a complete idea of what this true distribution mu looks like. So this is the optimization problem we want to solve, but we can't solve it because we don't know mu. So we do the next best thing. We say, well, instead of the expectation according to the true distribution mu, let's look at the expectation according to the empirical distribution that we observe. So this loss, L sub n, is basically just the empirical loss. So you add up the loss at each of the points xi and take the average. So now what we want to do is to say that this L sub n of ws is a loss function. We want to figure out what is the w that seems to minimize this and output that w as the output of the algorithm. All right, so now this is all right. So this is the most important slide of this talk, where I'm introducing what is meant by generalization error. And so I had not encountered this I guess definition of this generalization error before I started working on this, and I found it very odd when I first encountered it. So that's why maybe it's useful to spend some time on this slide. Right. So the first bullet point here says that this is just what we saw before. This is the expected loss. So, but the expected loss is taken over both the randomness of the x. So it's taken over the randomness of the, say, the cat images that you haven't yet seen, and it's also taken over this probability distribution of w. So the way to think of this is the following: that you have you have a data set S, which is generated according to P of S. After you look at P of S, you now run your algorithm, and the algorithm is going to generate a W condition on S. So the end result of this process is a W that has the marginal the same as if it were a W generated by running your algorithm on P of S on S. Okay, so we take that W, which has been generated according to the data set S, and then test it on something that it hasn't seen. Okay, so on the things that it hasn't seen are distributed according to the true distribution mu, and we take the expected loss. So this is what you could think of it as the test error. So W is something that was determined after looking at the training data, and then you take that W, you run it on stuff that it hasn't seen, and then just take the expected loss. So that's the standard, I guess, test error. What are we trying to do? Well, the way we are picking a W is to minimize the training error. So the training error here is, so this was the loss that I had before. And all we are doing is, this expectation is taken with respect to S and W. So we're trying to say that you want to generate a W after looking at S so that this expected loss is minimized. So this is train error, and the first term is a test error and the second term is a train error. And generalization error is defined as follows. So again, what we really want to minimize is this guy, the test error, because we want our algorithm to run well on stuff it hasn't seen. So this test error, which we can write as, which is the same as expected loss. So you can write it as, you can just add and subtract the same term, which is the expected empirical loss. And you can think of this as test error minus train error plus train error. So we haven't really done anything here. We just added and subtracted training error. And it turns out that this way of writing the loss as test minus train plus train seems to have some advantages while analyzing the performance of the algorithm. So in particular, this first term which I've written, the test error minus train error part, this is what is called as the generalization error of your algorithm. Okay, so I've just restated it here. The generalization error is the expected loss according to the product distribution minus the joint. Okay, so this will become a bit clear in a moment. But I guess the main takeaway is just this, that generalization error is some quantity that is trying to measure what is the difference in the performance on the training set and the difference in performance on the test set. So if your algorithm is performing really well on the training set, which means its train error is small, but it's performing horribly on the test set, then this generalization error will be a big quantity. So this quantity is small when your algorithm is performing about the same on both the test and the train set.
Varun, a quick question. Yeah. Are there trivial cases when this generalization error is zero? Like, for example, if you have, I don't know, like uniform distribution, will it be zero?
Yes. So there are trivial cases. For instance, you could have an algorithm whose output is always fixed. So it never looks at data. It just says no matter what the input, the output W is, say, some favorite W that the algorithm has chosen.
How about non-trivial cases where this generalization error is
zero? Oh, non-trivial cases. No, not that I'm aware of. Like, not that I'm aware of. Yeah. So there are lots of trivial cases in which it is zero. But I think in general, for non-trivial cases, you try to minimize this error as much as you can, but you also want to take care of the train error. So what you would ideally like to do is to make this term small as well as this term small. But I think for non-trivial cases are those in which this term is actually becoming small, and then this doesn't exactly become zero. The generalization error doesn't exactly become zero, but yeah. So I'm not aware of a non-trivial case where it is
uniform wouldn't become zero, and ergodic and like all the nice stuff, would it not go to zero?
It will be zero. So I'll get to some examples where it is zero. But roughly, one situation where it is zero is if you were to already know the answer W star, then so then generalization would be zero and training error would also, it won't be zero, but let's see.
Okay.
So basically for any fixed W star, it's going to be zero. Like if the algorithm is just not looking at data, then it will be zero. Yeah. Okay. All right. So this is the kind of the main definition, that you want test minus train to be small. And like I said, Salim pointed out, just making this quantity small is not really the end game, because the true, the quantity that we really should be interested in is this, the generalization error plus the training error. But for analysis purposes, it is often beneficial to analyze this generalization error separately and training error separately. But again, it's a caveat. Like just because the generalization error is zero does not mean your algorithm is good. It just means that the algorithm is performing just as well on test as it did on train, which means it could be performing really well on both, or it could be performing terribly on both. It just means it performs the same. Okay. All right, so the last line here is essentially rewriting the test and train error, but it's rewriting it in an interesting way. So it's basically saying that this error can be written as the expectation of the same function, this ln of ws, but once you take the expectation with respect to the product distribution, so you say S and W are independent, and once you take it according to the joint distribution. So recall that what is the joint distribution? Well, you look at S and then you run your algorithm, which produces a W based on that S. So these here S and W are of course related because your W is generated by looking at S. So this term is basically the training error, and the first error is the test error, where you've generated W according to the marginal of W, and then you run it on some data set S which it hasn't seen. So on the left you have the test error. Right. So so that's how this definition comes up. And now as information theorists, we kind of look at it and see, well, this is very reminiscent of mutual information, because mutual information is the KL divergence between the true distribution and the product distribution. So this seems like something that is trying to look at the difference of a loss function between the true distribution, the joint distribution, and the product distribution. So it seems kind of natural to try and use information theory, particularly mutual information, to say something about this quantity. And that's what, all right, so I guess I don't need to really go through the basics of information theory, but I'll just mention that I need only two properties in this talk. And one is the data processing inequality, which is if you have x to y to z, then ixy is greater than ixz. So information kind of decays along the Markov chain. And the second property I need is just the chain rule, which is mutual information between x1, x2, and y is first take the information between x1 and y, and then add the remaining information having found out x1. So it's x2, y condition on the fact that you know x1. So I'll only need these two properties in the whole talk. So so the start of this kind of line of work, so I found out about this line of work from this paper by Xu and Raginsky in 2017. And their result was the following: that under some assumptions on the loss function, which is that it's say well behaved, that it has very thin tails, then they showed that this quantity, the generalization error, happens to be upper bounded by something like square root of mutual information over n. And that's pretty interesting because this is a very different kind of a bound than what has appeared in the literature so far. So until then, there were bounds on this quantity on the left, the generalization error, but they used certain properties of stability of algorithms. And what was different about this bound is the notion of stability they were using was very different. They call it the information-theoretic stability, and it's different from what people had studied prior to this. And second was that their bounds are also data dependent, which means that this quantity R, the sub-Gaussianity, kind of depended on the data. The mutual information also depended on your data distribution. Again, the previous bounds that people had up to this point were not data dependent; they were purely algorithm dependent. So that was something that was interesting about this paper that I thought was quite interesting. And so I'll skip the proof sketch, but essentially what it does is you try to use a characterization. You use the fact that mutual information is KL divergence between the joint and the product, and then use a certain variational characterization of this mutual information, saying that it's the supremum over all functions f of this particular integral, and you plug this definition of KL divergence being a supremum of something into the mutual information formula, and somehow pops out this kind of a formula. Okay, so this is not a very difficult to prove theoretically, but it's a very neat observation. And all right, so here's what we were trying to do. Well, we have this result which says that the generalization error is upper bounded by mutual information between W and S. But how are we going to use it? And that's because if you're given an algorithm, say stochastic gradient descent, well, how do you compute the mutual information between what you started out with, the data set S, and where you landed, which is your point W? Okay, so that's a pretty, it seems very abstract. Like if there is no way to compute this mutual information or bound this mutual information, then you can't really use this bound. Okay, so that was kind of our motivation, that how we want to use this mutual information bound, but how do we start using it? And kind of the key insight is, well, most algorithms are iterative, which means you don't just produce this W out of thin air. You start with some initial point W0, you do some update rule, you get W1, you do some another update rule, you get W2, and so on, and you do it until a certain time t, and then you stop. Okay, so most algorithms do in fact run like this. Starting from some point, you go and descend. Maybe you're trying to minimize this loss function, and then you'll end up at some final iterate WT, and that's your output. So of course, what we want to bound is the information between this final guy maybe and the entire data set. But perhaps, all right, so I guess what I've written here is you don't really have to have it to be the final point. It could also be an average of all the points you have encountered so far, or it could be any arbitrary function of the iterates that you have seen so far. Okay. And so the idea that we had was we want to bound IWS. So let's try to control it by controlling the information at each iteration. So roughly, we are trying to say that you start from W0, you end up at WT. And if you could somehow bound how much information there is in each iteration, you could add up all these chunks of information and get that the total information between where you land up and the data set S has to be upper bounded by some reasonably easy to calculate quantity. Right? So that kind of was the idea, that let's try to look at stepwise mutual information and try to get bounds on that. Okay. So we decided to use this class of algorithms, which we call noisy iterative algorithms. And if you have seen stochastic gradient descent before, then it's basically the same as stochastic gradient descent, but with one tweak. Okay, so the first three bullet points are so the first bullet point says you're sitting at a point W, WT minus 1, and then you look at your some random sample from your data set. So this random sample, let's say, is ZT, and you figure out which direction you want to move in. then you figure out some step size eta t, you move in that direction. But once you move in that direction, you do something really odd. And that odd thing is you deliberately add Gaussian noise to it. Okay, so the overall update equation is here that if you're sitting at Wt minus 1, you figure out this direction, which is f of Wt minus 1 ct. You move in that direction, then you add noise. Right? And
but I have a question, because on our side you got cut off for a short time. So why you're adding the noise?
Sorry? Sorry?
Yeah, why are you adding the noise?
Okay. So I will. Yeah, that's a really great question. So the reason we are adding noise is it improves generalization performance. So what we really want to do is we want to bound the information between where you land up and the entire data set. Bound means we kind of want to make sure that the information is not too large. And one way to ensure that it's not too large is to deliberately add noise so that your algorithm does not rely too much on the data set. So it is roughly moving in the correct direction, but it's not relying too much on the point that it saw. So deliberately adding noise is one way of reducing the mutual information between your output and the data set.
So basically you're tightening the bound, or do you also...
Sorry?
Are you trying to find the tight bound, like kind of tighten the upper bound that you have, or this is?
So we're trying to. So I'll go. So the algorithm that I kind of the main example of an algorithm is the stochastic gradient Langevin dynamics, which I'll explain on the next slide. But essentially, this is what all those kinds of algorithms do. But their aim in adding the noise is a bit different. So often when you're trying to minimize a function, you try to add noise, or you take a random step in order to escape from local optima. So if you happen to be stuck in a local optimum, then you deliberately add noise so that you jump out of it, and then you can explore the space better. But so it seems that another motivation for adding noise could be that you just want to improve the generalization performance of your algorithm.
By the way, do you have any analysis on the maybe error for the end? Because when you add some noise into it, maybe it's not convergent to the global minimum, right?
Yeah. So what I would do is look at analysis for say, and in the analysis, people have figured out what the eta t should be and what is the variance of the noise that should be added. And what I'm going to do is to just use the eta t and noise variance that people have already figured out work, and plug into whatever formula whatever bound that I'm going to end up getting. So so my job won't be to figure out what the perfect eta t and psi t are. I'm going to leave that to the person who is designing the algorithm. And once the algorithm is designed, then what our theory will tell is how well is that algorithm guaranteed to generalize. And I will give a few examples for why this class of algorithms is not is fairly big. So there are a bunch of algorithms that fit exactly in this class of algorithms, and their motivations, as I said, are often different. It's not about minimizing generalization error, but it's more about escaping local minima. But for whatever reason, they wanted to escape local minima, so they figured out a certain eta t and psi t that work. And what we can say is that, well, for that eta t and psi t, this is how well your algorithm will generalize. Okay. All right. So we do have a bunch of assumptions. So I'll very quickly go through them. One is we need the assumption of sub-Gaussianity, which is the same assumption that Raginsky and Shu had. And the second assumption is we kind of assume the updates are bounded. So if you're sitting at a particular W, then if you happen to see some new point Z, then you don't move too far away. That there is some distance L you'll move at most L away. So you can think of it as a clipped gradient descent. So if the gradient just happens to be too big, you just clip it at some value L and then move it there. And the third assumption, which is kind of crucial, is that so in stochastic gradient descent or in any kind of iterative algorithm, the new bunch of samples that you see, which we are calling as zt+1. So at time t, you observe zt+1 and then figure out which direction to move in. The assumption that we have here is that this zt+1 is sampled without looking at the history of how the algorithm has, how the iterates have behaved so far. And that is kind of natural, because if you were to choose which future point you want to look at based on how the algorithm has kind of descended so far, then you might have you have a lot of power to influence where the algorithm might go in the future, because you figure out, well, I want the iterate to move in this direction, so let me pick a ZT that makes it move in that direction. So you are not allowed to do that. You have to pick a ZT+1 without looking at the W's. So you're allowed to look at the Z's, but you can't look at the W's, which is, you can't look at the output of the algorithm to figure out where you're moving next. And so I'll skip this slide, but this is just saying there are a lot of conditional independence properties that are going on in this model. So we have a lot of random variables, and all those conditional independence results can be summarized in this one graphical model kind of a picture. And all right, so here's our main result, that in these kinds of algorithms where you have an iterative structure, this mutual information between W, which is your output, and S, which is the data set, can be upper bounded by this term on the right. So just recall that this eta t was the amount of noise, was the step size that we are adding. Sigma t square was the amount of noise that we were adding. D is the dimension. And there is this summation term which goes from 1 to t, where t is the amount of time you ran the optimization procedure. And so clearly this bound depends on t, which is kind of natural, because the longer you optimize, the higher the risk of overfitting, because you're trying to minimize this empirical risk function. And the longer you optimize, the more likely that you're going to find a minimum that is really well optimized for that particular empirical loss, but it won't generalize well. So you might be overfitting. And yeah, and another thing I want to point out is that we have a summation from 1 to t. And again, the origin of the sum is because we are trying to bound mutual information in each step. And the quantity that I've written inside the bracket, the d by 2 log of something, is essentially how much information is there in each step. So in t steps, you can have at most this much information. So that's how we get the bound on the right. And there are a bunch of implications. So one is that once you can bound mutual information, we can directly use the result by Raginsky and Chu to say that, well, this is a nice bound on the generalization error. And the second part, well, you can kind of ignore it, but what it's saying is that Raginsky and Chu also had a high probability bound. And pretty much everything that we have goes through. So all we need is this bound on the mutual information. And once you have a bound on mutual information, you can plug in and also get like a high probability bound on the loss, or rather the generalization error. All right, and so I'll go through applications. So this is kind of the relevant part. So so the most the ideal example that we had in mind was the SGLD. So that stands for stochastic gradient Langevin dynamics. So what happens in this is pretty much exactly what happens in our class of algorithms. That you're sitting at a WT, you figure out to which direction to move in by taking the gradient of the loss function at some sampled point ZT. You move in that direction, and then once you move in that direction, you deliberately add noise. Okay? And so the SGLD was in fact proposed for the purposes of sampling, not exactly optimization, but now it is also used for optimization because it has this added benefit of escaping from local minima. Okay. So there are a bunch of common choices that people use for sigma square, the length of the algorithm, the amount of time you run it, and what the step size should be. So again, as I said, like it's what our result is going to do is that it's just going to look at what is the eta t that you want, what is the sigma that you want, what is the t you want, and we are going to just plug it in and say, well, for if you're going to use SGLD for your optimization procedure, this is what your generalization is guaranteed to be. So it's something like 1 over root n, and it scales like square root of the log of the time. Another example.
Another question. Among these things, which one do you think would have more effect on this bound? Like, should I invest in optimizing the step size or the noise, or which one would give you more bang for the buck?
Okay. So maybe so the last bullet point is then more relevant for that. So both this bound that we have obtained is like it's a bound, and you might try to optimize that bound, but it won't be. There may not be too much a point in trying to optimize it because it's not tight. Okay. So the best known bounds for SGLD are in fact order 1 over n. So what we have is like 1 over square root n, which is not as tight as 1 over n, but there is some advantage for using these bounds because they're information-theoretic bounds, so they are extremely general. So the W that we are producing at the end can be any arbitrary function of the iterates, and it doesn't really have to be the last iterate, which is what some of these works have tried to do. So yeah, so my opinion would be. I don't think we can do better because these quantities sigma square and t are kind of already optimized to make sure that it converges. So yeah, I don't think there's too much benefit in like playing with these quantities because we could accidentally end up making the generalization error small, but the training error might blow up. So yeah, these choices of sigma square and time and step size are kind of optimized for the training error plus the generalization error both to be small.
And do you know what, like roughly, I mean, really high level, the 1 over n, how is it proven? Yeah, like is it different?
Yeah, so the 1 over n is proved using stability argument. So so as I said, this information-theoretic stability is a bit different, but the standard notion of stability is if you have an input data set S, and if you were to take one point in the input data set and change it, so either modify it arbitrarily or maybe just even delete it, then how much does your output change? So what Moe et al. Did in their paper was they looked at something like the Hellinger distance between the probability distribution of W given S, which is the original data set, and W given S prime, which is like the one element perturbed data set. And they showed that this quantity can be used to control the generalization error, and they basically bound that quantity.
Okay.
Yeah, but it's very algorithm specific because that bound really looks at the guts of how SGLD works and then produces this bound of 1 over n. So I guess one advantage here is that you don't really need to know too much specifics about the algorithm. It just gives you a bound of 1 over root n without knowing a lot about the algorithm. Okay, so one more. So this was another recent paper by.
I have a quick question about the Moe et al. Result. Is that tight?
That's tight. Yeah.
Okay.
So by the way.
Sorry.
By the way, I'm still not very clear why you choose a noise variance sigma t square as epsilon t, because I think you don't need to make it convergent, right? Because when, for example, you have large sigma t for the noise variance, maybe it's not convergent, so it will have some bias on the training error, but you will achieve a better generalization error. So there will be a trade-off, maybe.
That's so you could have a huge amount of noise, and you could actually excellent generalization error. But if you actually do care about the training error as well, then you would be less inclined to have a big noise, because it means when the higher the noise, you're kind of relying even less on your data, which means the W that you end up producing may be pretty bad, because you essentially did not look at data at all. So yeah, so there is a trade-off between these two kinds of errors, and these quantities that were chosen, I guess the eta t and the step size and the noise, were to make sure that the trade-off, it's kind of optimizing, it's balancing both those terms for this model. Okay, so another example is this a perturbed stochastic gradient descent algorithm, which was proposed to escape saddle points. And in that, the algorithm looks essentially the same, except the noise is a bit different. In particular, this algorithm is a lot less noisy than the stochastic gradient Langevin dynamics. But as far as our theory is concerned, we don't really care. Like as long as it fits into the class of algorithms that we're looking at, we can just apply the theory. But of course, the bound that we get will depend on what is the kind of noise. So in this case, you get a mutual information bound which scales linearly with time. Earlier, it was scaling like square root of a log of time. So that was a bit different. And here, of course, there is no n here. So this quantity might just is in fact going to increase to infinity. So your bound is going to get worse and worse the longer you run the algorithm. Okay. And so once we have mutual information bound, then we can just plug in and get bounds on the expected generalization error and some high probability bounds on that on the same. And all right, so in the interest of time, I'll just skip this, but there is another example where we can use the same bounds. Okay. I'll also basically skip the proof sketch, except I'll just focus on the last line, that mutual information between the iterates, between the sampled points and the iterates can be written using the chain rule. And you can look at the expansion in the chain rule and use all the Markov chains that we had in the graphical model and get like this very simple expression on the right. And the expression on the right is saying that, well, the total mutual information is basically the sum of these stepwise mutual informations. And the way to interpret the stepwise mutual information is you're sitting at this point, WT minus 1, and you're trying to, and then you look at a point ZT and then move to WT. So it's saying that if this term is basically small, then it means that the starting from WT minus 1, you aren't relying too much on the ZT to figure out where you move next. Okay, so if you basically bound this quantity, which is like the stepwise information, then you get a bound on the entire mutual information. All right, so, and what we essentially do is use like fairly simple bounds in terms of Gaussians being the maximum entropy distribution for a fixed variance, and plug them into the one-step mutual information and get the bound on the last bullet point, which says that the stepwise information is bounded by the quantity on the right. And of course, our overall bound just turns out to be a summation of the terms that are on the right hand side. Okay, so yeah, that's it. So in the last 10 minutes, I'll just explain. I suppose, well, mutual information is great, but there are some reasons, as I said earlier, for not wanting to use mutual information. And that's because, in some cases, this mutual information IWS shoots up to infinity. In particular, if you have a deterministic algorithm, so an algorithm that looks at S and produces a W which is deterministic, then this mutual information is infinite. And then then our bounds are pretty much useless, because we are trying to bound this error using mutual information, and the right-hand side mutual information is infinite, so you get a bound of infinity, which is pretty useless. So, and in particular, what really bugged us was that you can't use this bound even for standard stochastic gradient descent. So you can use it for the Langevin dynamics, but you can't use it for stochastic gradient descent, again because of this kind of same issue that mutual information happens to shoot up to infinity. And so just thinking like there has to be some way to use these ideas, but even apply them to regular stochastic gradient descent, or to cases where there is a deterministic output based on the input.
Varun, I have a question. So would you be able to elaborate more why you have this problem of the KL divergence going to infinity in the case of?
Oh, sure. So I guess the simple thing is following. So if you have, let's say you're trying to find a mutual information between a continuous random variable x and some function of x. So let's say f of x can be x squared or anything, but let's just say f of x. So mutual information between x and f of x can be written as entropy of f of x minus entropy of f of x condition given x. So of course, entropy of f of x would be some finite number, because I mean it would be some number. But then you go to the other term, which is entropy of f of x conditioned on x. Now, conditioned on x, f of x is completely known. Like there is no randomness in f of x, and it turns out that the this entropy term is therefore negative infinity. And therefore, when you try to write what is I of x comma fx, that turns out to be positive infinity. So for deterministic algorithms, it just shoots up to infinity, and so roughly the same story holds for stochastic gradient descent as well. That if you are starting with some data set S, and if there are only, say, countably many W's that you could hope to produce after starting at that, starting at that data set S, then again you get this same issue that mutual information is infinity, because the output distribution is kind of not absolutely continuous. It has these atomic measures on the space of W.
Okay.
That's sort of clear?
Yeah.
Okay. All right. So I said that these noisy algorithms are kind of good for improving generalization error, and also for escaping local minima and everything. But it turns out these algorithms are also essential if we want to even try to use these mutual information based bounds, because otherwise we just get an infinite mutual information, and that just makes everything useless. All right, so 5 minutes. So I'll just explain what the proposed fix to this thing is. So we tried to use what is called the Wasserstein distance from optimal transport. So roughly what this distance means is that if you're given one distribution mu and another distribution nu, then the Wasserstein distance is something like, just think of it as some notion of distance in the space of distributions. So for example, something like total variation is also a notion of distance. But say Wasserstein is a more, well, it kind of uses the underlying metric space to determine what that distance is. So it's a bit more involved notion of distance, and turns out to be extremely useful in analysis and in geometry analysis, and also in the recent years it has also shown up a lot in information theory, kind of inequalities and stuff. Okay. Okay. So the good thing about Wasserstein distance is it's always finite. It doesn't ever blow up to infinity. So so I'll skip this slide. I'd say, all right. So we had one assumption. So let's just say you assume that the loss function is Lipschitz. So instead of the sub-Gaussian assumption that we had for mutual information, now we just have an assumption saying that the loss function is Lipschitz. And if you make this assumption, we get the following bound. Okay, so the bound looks fairly ugly, but the point is just the following, that if you look at this integral, the way the integral is working is you're looking at some notion of distance between P of S, which is the input distribution, and the conditional distribution P of S given W. So you're trying to kind of, this is something like variance in the space of distributions. Like if you think of it that way, like it is looking at what is the distance between P of S and P of S given W, and kind of averaging out that distance over all P of S given Ws. And turns out showing this bound is not very hard. It just uses some coupling properties of the Wasserstein distance. So you can end up with a bound which looks fine. And the nice thing is it doesn't blow up to infinity, and it's always well defined. The difficult thing is, well, how do you compare it with the mutual information bound? Because we can't, if we can see that this bound is better, then yes, we should always use it. If this bound is worse, then we should not use it. Turns out you can't always compare it, but in some very special cases, you can compare it. So there is one transportation inequality which is called the Talleyrand transport inequality, which says that, well, sometimes you can bound Wasserstein distance by KL diversion. Okay, so I won't go into the details of sort of when, but roughly if mu is if mu is a Gaussian distribution, then you can do that. Okay, so you can bound Wasserstein using KL, and so I will also skip this and just say that in general, the mutual information bound is not comparable. But if you have that transport inequality, then you can basically show that the Wasserstein bound is always going to be better than the mutual information bound. And that's kind of a relief that this is a more complicated looking bound, but at least you can show that in certain cases of interest, it's strictly better. And not only that, you're kind of guaranteed that it will never run off to infinity, so it will always be something finite. So even if we are using SGD or any other kind of a deterministic algorithm, the Wasserstein bound will always be non-infinity. Of course, the difficult thing is, well, how are you going to compute it? Because now we no longer have very nice properties of mutual information like data processing inequality or chain rule. So that makes the job a bit hard. So we haven't really figured that out yet. So we just know that there is this bound, but we don't really know how to compute it in cases of interest. So I'll skip the proof sketch and jump straight to the speculations. Okay. So I said that in the beginning, there are these two kinds of problems, the forward problem and the backward problem. The forward problem is get the curve looking at the points. And the backward problem is get the points after looking at the curve. Okay. And so this notion of stability, which people have studied, is kind of like asking how much does the W change? How much does your output change if your input changes by a little bit? Okay, so what you can think of this as a property of the forward channel, that the forward channel is kind of determining how stable your algorithm is. Generalization seems to be a property of the backward channel. So looking at the bounds that we have, the Wasserstein bound as well as the mutual information bound, they both seem to suggest that generalization is like how much does the S change when your W changes a little bit. So it seems to be like a property of the backward channel. So there might be, so this is just a very high level, I don't know, not even a very deep observation, but it just seems like, well, stability is forward, generalization is backward. Sometimes stability and implies generalization and vice versa, because roughly if the forward channel is noisy, then the backward channel is also noisy. But maybe you can use this interpretation to pre-process the data to deliberately make the backward channel noisy sometimes, and maybe that will increase your generalization performance. Another speculation is this whole theory has to be related to rate distortion theory in some concrete way. Because in the rate distortion theory, in information theory, we really basically do the same thing. We try to minimize distortion subject to some mutual information bound. So the mutual information bound is going to determine how well your algorithm generalizes, and the distortion is the training error. So you kind of want to minimize the training error subject to a reasonable generalization error. And so the problem looks very similar, but the settings are a bit different. In that the standard theory for rate distortion is that the distortion function is kind of separable in the form that I've shown here, but that's not really the case for the loss function that we encounter in this problem. So yeah, but there must be some deeper connection between rate distortion and this generalization error theory. Right. All right. So we have a bunch of open problems that we are working on. Most of them deal with, well, we have this Wasserstein bound. What do we do with it? Because we can't really evaluate it in specific cases of interest. So that's kind of the future work. Like what we have this strange quantity which looks like mutual information, but it's not really mutual information. It's like the Wasserstein distance between the joint and the product distribution. So we don't really know what properties it satisfies. So that's something that we hope to work on. And yeah, that's about all. So, thank you.
Thanks a lot, Varun. So I don't know if people have questions, they can ask you. If anyone has questions.
I will stop the screen sharing.
Yeah, I think if no one has questions, because I think we asked enough questions during the talk. So we conclude here, and we'll want to thank you again.
All right. Yeah, thank you. Thank you for inviting again. It was a very different experience. Thank you.